Here are some solutions for week 4's homework assignment. We are assuming that y is not a vowel in this problem. A is a set of vowels, so that's A, E, I, O, U. And B is all the consonants, so there's 21 consonants. And C is the set of letters of the word people. Now notice there are 6 letters in the word people, but there are some repeats. So C has only 4 elements in it. That's something to keep in mind. It has P, E, O, and L, and that's it. Express set A using set builder notation. X, well, here's one way to do it. A is equal to the set of, right? A is the set of all elements such that that element is a vowel in the English alphabet. Now you could put really any symbol you want here as long as you put the same symbol right there. You can use X, you can use Greek letters, you could use different letter, you could put a happy face, whatever symbol you want. Express the set A minus C using set builder notation. So in order to be in A minus C, we need to be in A but not in C. So A minus C is the set of all elements. Again, any letter can go here as long as the same thing goes there, or any symbol for that matter. The set of all X such that X is a vowel but not in the word people. And there are a lot of ways you could have said this. You could have said such that X is a vowel but not E or O, or such that X is a vowel but not in the set C, right? Lots of different ways you could have expressed this that are reasonable. I also drew a little Venn diagram here of the letters involved in sets A and C, and I shaded what A minus C looks like. Everything that's in A but not in C. The cardinality of the set C is only 4. Remember, even though people has 6 letters in it, 2 of them are repeated, so there's only 4 elements of C. And these are those 4 elements right here. So we can do n of C, that means the number of elements of C, or other notation you could put C in these vertical bars, talks about it, that refers to its size, its cardinality. Find the cardinality of the set B. Okay, so here's a little Venn diagram I drew of B and C. The cardinality of B is 21. There are 21 consonants, counting the Y. Cardinality of set C is 4. And in my Venn diagram, I put the only elements that were both in B and in C are the P and the L. And if we're going to do the set of B minus C, then we're talking about the cardinality of this portion of the Venn diagram. Like how many elements are here in B but not in C? Well, there are 2 elements in their intersection. That's what this comment is saying, the P and the L. And so the number of elements in B minus C would be 21 consonants minus the P and the L, and give us 19 consonants. All right, so I'm going to redo the shading here for a visual for my thought process. Shade the Venn diagram corresponding to the set A minus B, and then union with C complement. Well, A minus B is everything that's in A, but that's not in B. So, sloppily, it's just this part. Everything in A, but not in B. And then we're going to union that with C complement. Well, C complement is everything that's not in C, but in the universe still. Let me make this a little bit larger. So everything that's not in C, but still in the universe. You get the idea. I get a shade in everything that's not in C. And when I do a union, I'm going to keep anything that was shaded at least once. If this were an intersection instead, right, if it were this symbol, then I would keep only this portion right here that was shaded twice. But because it's a union, I'd keep everything that was shaded at least once. And in the end, that wound up being A minus B union with everything not in C. A minus B union. Okay, I think it was, here's A minus B shaded. And then now I'm going to join that with anything not in C. Okay, so we get this shading. Sometimes it takes a while to do the shading, but here we go. And this is what you should have shaded in for that. The next one was B complement minus A intersect C. Let me do A intersect, oh, let's do B complement first, whatever. So I'm going to shade everything that's not in B. Okay, you get the idea, everything not in B, but still in the universe. And I'm going to shade now A intersect C, that's this part right here. So we're going to begin with, there's the B complement, and I'm going to remove from it, the set subtraction, anything that's in A and C. So I'm going to take this football shape out away from what's currently shaded. So that's going to really just wind up removing this part right here will get removed from what's currently shaded. So in the end, we get the complement of B, but then remove that part of that football. And then the complement of B. Okay, so we wind up with something that looks like this. And you can take your time and make your shading a little bit better than what I've done here, but you wind up with this portion. Write an expression using a set difference that represents the shaded portion below. Well, it seems pretty clear that we have, started with B, but then I removed this little portion right here. This needs to get removed from B. So in both of my solutions here, I wrote two different ways to do this. I started with B, and then I'm doing set subtraction or set difference. And you can either remove, you have a few options here, maybe even more beyond what I did. But initially, this first one right here is removing this football from B. Now, of course, only a part of that football was in B to begin with, but we start with B, and then we remove anything from that football from B, and that gives us that portion there. Or you could target very specifically, right? Just start with B, but remove only this portion, which is what this bottom one is saying. Start with B, and then just remove the intersection of all three. So a variety of ways. Number 3. Okay, so I put a solution down here already, but I made a sort of a table out of this problem where I considered every possible way that two sets could interact with each other. Now, it's possible that two sets are the same in general, right? So it could be A and B are the exact same set. However, the cardinalities of the two sets are different. That tells me that they can't be the same, so this whole case just go away. It's also, so the other possibilities are that the two sets are disjoint, that they have some overlap but also some distinct elements, or that one is entirely in the other. Now, is it possible that B was the superset and A was a proper subset? Is this possible? Well, not given these cardinalities, right? B has to be smaller than A because it has a smaller cardinality. So A could not be a proper subset of B, so we get rid of that case. So we really only have 3 cases here. All right, the 3 columns. Either they're disjoint, they have some elements in common, but also some distinct elements, or B is entirely inside of A. And then I considered, okay, so what would be the union in each of these cases? Right, so in the case of, let's go a little bit smaller this time. There we go. When you're doing a union and they're disjoint, you just keep everything in one or in the other. So whatever their cardinalities were, separately, this had a cardinality of 7, and this had a cardinality of 4 elements in there, then their combined cardinality would be 11. The union in a case where they have some partial overlap would just be shade everything in A or in B, so you just get to shade the collection there. And here we had some possible things to consider, like what would happen if there was only one element in their overlap. That would force 3 elements in B and force 6 elements. Let me say that again. 3 elements would be in B but not in A, and 6 elements would be in A but not in B. And you can see here that this gives us a total of this 10 total cardinality for the union. What if there were 2 elements in their overlap? That would put 2 elements in B but not in A, and 5 elements in A but not in B, and that would give us this 9 total cardinality. And then what if there were 3 elements here in the overlap? That would put 1 in B, and there would be another 4 over here in A minus B. And that gives us a total of 8 elements total in their union. And then you might say, well, what if there were 4 here? Well, that would force 0 in the B minus A portion, but that's really just this case again, so I don't consider that option. So these are the only possible cardinalities of the union given this situation. And then finally, over here on the right, if B is entirely in A and you do their union, then you wind up just keeping anything in A or in B. So you wind up just getting everything in A shaded again, and that cardinality was 7. So the question was, what's the maximum possible cardinality when you do a union of these two sets? And the answer for the max would be here at 11, and the minimum possible cardinality would be 7. Now when you do their intersection, we have different results. When you have disjoint sets, the intersection is the empty set. Right? There's nothing here to shade that they have in common, so the empty set has a cardinality of 0. When you have this situation here, we have the intersection is what the overlap, and that, as we saw from above, could be 1, 2, or 3. So that would be the cardinality of the intersection, either 1, 2, or 3. And then over here, when B is a subset of A, and you do their intersection, the only things they have in common are the things that are in B, which had a cardinality of 4. So for the intersection, the smallest cardinality possible is 0, and the largest cardinality possible is 4. A minus B. Okay, so let me hide those shadings. When you're disjoint and you do A minus B is everything in A, but you have to remove anything that might be in B as well. But when they're disjoint, there's nothing in A that's also in B, so A minus B just is A. In this case here, we get A minus B is this portion of the Venn diagram, just over there, anything in A but not in B. And over here, anything in A but not in B is going to be everything in A but not in B. So you just have to remove the inner circle. You have to remove the B set from A. Right, so you get something like this. And now for our cardinalities, right, this had a cardinality of 7, so our cardinality of the shaded part is 7. Here we had cases again, right? If we had 1 overlapped, then there would be 6 in that portion. If we had 2 overlapped, then there would be only 5 in this portion. And if we had 3 in the overlap, there would be 4 in that portion. So the possible cardinalities of the shaded portion are 6, 5, and 4. And then over here, we had 4 in the shaded portion because there's 3. Let me take that back. There'd be 3 in the shaded portion because there's 4 in the set B, and that 4 got removed from the 7. So there's only really 3 left in that shaded part. So in here, when we do A minus B, the max would be a 7 and the minimum would be a 3 as far as possibilities are concerned. And then finally, if we do B minus A, the shading that we have would look like this. B minus A in the case of disjoint would just be B. B minus A would be the portion of B that doesn't involve A. And then over here, if you do B minus A in a case where B is a proper subset of A, you start with everything in B and remove everything that's also in A. Well, that means you're going to remove everything. And so you have the empty set in B for B minus A over there. And so our cardinalities are, right, this had a cardinality of 4, and that's all that's shaded. Here we had possibilities, if you recall. If there's 1 overlap, then there would be 3 in this portion. So 3 is a possibility. If there was 2 in the overlap, then there'd be 2 in that portion. And if there was 3 in the overlap, there would be 1 in that portion. So 3, 2, and 1 were the possible cardinalities of the shaded portion. And then 0, of course, is the cardinality of the empty set. And so 0 is the minimum, and 4 is the maximum possibility when you're doing B minus A. Number 4. You toss a coin, and then you toss a die, a 6-sided die. So A is the set of all possible outcomes for the coin costs. So A could be heads or tails. That's it. B is the outcomes of the die toss. So it could be 1, 2, 3, 4, 5, or 6. And then we're going to do a Cartesian product. Let me skip down to D. The Cartesian product is defined to be a set of ordered pairs. So when you do A cross B, you make ordered pairs where the first coordinate is something from A, and the second coordinate has to be something from B. So here's a few different ways of writing the set builder notation for this particular Cartesian product. In fact, this is one that's true in general. It doesn't matter what A and B are, but this one was a little more detailed, specific to what this particular A and B are. And so visually, all that's really happening here is you're saying, okay, I'm going to make ordered pairs where the first element is something from A. So you could do H with the 1, H with the 2, H with the 3, H with the 4, H with the 5, H with the 6. And then you just repeat. Do the T with the 1, T2, T3, T4, T5, T6. You get all these possible ordered pairs, which are listed actually right here. But because of the multiplication principle, if you have 2 options here and 6 options here, then you're going to have 12 overall options, right? You multiply those two numbers. And here's a listing of those 12 ordered pairs. Now remember, each element of a Cartesian product is an ordered pair. So this is considered a single element. And there are 12 single elements, even though each element is an ordered pair of 2 elements. Okay, let's look at number 5. You have a decimal number, 3,725. Explain the meaning of each of the 4 digits. Well, the 3 is how many thousands there are, the 7 is how many hundreds there are, and the 2 is how many tens there are, and the 5 is how many ones there are. So each place represents a different value. Express the number as a combination of powers of 10. So that's what I've done here. This 1 at the end could be thought of as 10 to the 0. So you can see that every single thing in parentheses is a different power of 10. 10 to the 0, 10 to the 1, 10 squared, 10 cubed, etc. Oops. There we go. But 10 to the 0, often you just keep that a 1, 10 to the 0. Make a place value table. So this is pretty similar. You just put 3725 in this table. And you could also, instead of putting numbers in there, sometimes people will do this for place value tables, right? You'll put 5 dots in there. That stands for the 5 ones. 2 dots in here stands for the 2 tens. And then we had, 7 hundreds? 1, 2, 3, 4, 5, 6, 7 hundreds. And then we had 3 thousands. So either putting numerals in there or dots in there, whichever. Oh yeah, this asks specifically with an appropriate number of dots. So let's make sure we get the dots in there. Explain the meaning of each box. Right, this stands for the number of dots in here is how many ones, how many tens, etc. Okay, so then we express this number using base 10 blocks. Well, I did some copying and pasting to get these symbols, to repeat the symbols that were already provided. Right, if you recall that these here were already provided in the document, and I just copied as necessary. So we had 3 thousands right here. We had 7 hundreds right there, 2 tens, and 5 ones. So here's a representation for how big this number truly is. If you were to count how many single dots there were total in this whole collective image, right, you would have this 3,725 of them. Number 6. All right, so this was to fill in the table. I'm going to do this row by row. In the first row, we were given a base 10 number of 91, so what we're familiar with, 91. We're asked to represent that in base 2. Now, when you do this, you actually work from left to right. Now, base 2, I'm going to use place value table for this. And in base 2, you're only allowed to have zeros or ones in each box, either no dots or 1 dot, in other words. And each box represents powers of 2. So we have the ones, then we have the 2 to the first, 2 squares, right, 2 cubes, etc. So just keep doubling as you go from right to left. And if you were to keep going, the next box would be 128, although I didn't include this because if I put a dot in here or put a 1 in there, then that would represent that we have 128, but that's already more than this 91. So we only go as far as we need to, in this case 64. So we definitely need a 64. We'll put a dot in there. If I put a dot here as well, that would be 64 plus 32, that's 96. Well, that's too much. It's more than 91. And so I don't need any dots there. How about a 16? 64 plus 16, this adds to 80, so that stays below 91, so we're still good. We can add 8 to that, that makes 88, so we're still below. But adding 4 to 88 makes 92, that's too much. So to 88, we're going to add this 2, that makes it 90, and then also add this 1 to make it 91. So we have turn the dots into numerals, if you will. One dot, the dots are ones, and then an empty box would have a 0. So 1, 0, 1, 1, 0, 1, 1, and there's our base 2 number. Okay, in base 5, in fact, let me go ahead and delete a lot of these entries already so we can rethink these. So pay no attention to the numbers behind the curtain. They are not there. Let's delete some of this stuff. I've worked through these already once. Actually, I made a video already once, but the video didn't save for some reason, so I'm redoing. Let's get rid of some of this information, and we'll recreate. All right, so these place, as you can see from this image, these place value tables are very useful. Let's go to base 5. Base 5, you have powers of 5 as you go along the bottom. That's what the boxes represent. How many 1s, how many 5s, how many 25s. 5 times 25 is 125, so that would be the next box, but 125 is already more than 91, so you don't need that box. Okay, so keep in mind that we're still trying to do a base 10 number of 91 is what we're trying to create. How many 25s go into 91 without going over the net? Well, 2 of them is 50, so we need more. We need 3. You could do this with dots if you want. You could put 3 dots here and say that represents 3 25s. And that makes it 75. Or if you want, you can just go ahead and put a numeral in there. So we have 3 25s. That's 75. Well, that leaves, we're trying to create 91, if you recall. So that means we need 16 more. So we could put 3 5s. That's 15 more. And then we need 1 1. All right, so we get this 331 as our base 5 number. 331 in base 5 is the same thing as 91 base 10. Let's do base 6. Keep in mind we're trying to create 91. Well, 36, we need 2 36s. That'll make 72. Another 36 would bring that up to 108, which is too much. So 2 36s. That means we're at 72. Then we need 19 more, right, to get to 91. So how many 6s go into 19? Well, 3 of them. That makes 18. We have 1 left, so we need an extra 1. So 2 36s, 3 6s, and 1 1 will make 91. So our base 6 number is this 231 that we see there. All right, so in the second row, we were given this base 5 number. So the base 5 number given was 341. So here's a base 5 table, and here's 341. This means we have 3 25s, which is 75, plus we have 4 5s, so that's 20, and we have 1 1. So this gives us a total of 96, that in base 10. This is our base 10 number, so I fill that in next. Now I'm trying to recreate I'm trying to create 96 with base 2 and base 6. Okay, so to create 96, we definitely need a 164. And, a 32 makes the 96, and we're already done. So that means I don't need anything right in these other boxes. So 1 1 and then 5 zeros will be our base 2 representation of 96. 1 1 with 5 zeros. Now these zeros here are certainly necessary to write because they help establish the place value of the 1 and the 2 1s. But if you don't need to put zeros, lead off zeros, right? This was also true for base 10, right? The 0 here is important. The 0 here is not important. When you're working with base 10, that's true for all bases. The zeros after the fact matter because they help establish the place values of the non-zero digits. Base 6, all right, keep in mind we're trying to create 96, that's our goal. So 3 36s was too much still, so 2 36s takes us to 72. I need, how many more? 24 more. Well, 4 6s will get us to that 24, and that's all we need. And so we don't need any 1s. So 240 in base 6. So here's our 240 in base 6. And now let's go to the third row. In the third row, we were given a base 2 number, 1101. So let's, third row, we have 1101 as the base 2 number. This means we have 18, 14, and 11. So that gives us really just 8 plus 4, no 2's, but a 1, and we get 13. 13 is our base 10 number. Now we want to make 13 out of base 5 and base 6. Our goal here is to make a 13 out of these two tables here. Well, we don't need any 25s, it's too much. We need 2 5s to get to 10, and then 3 1s. So just 2 3 in base 5 is the same thing as 13 in base 10. Notice when I say 2 3, I don't say 23. As soon as I say 23, I'm implying that we're in base 10, but 20 means 2 10s. So make sure you say this as 2 3 in base 5. It means 13 in base 10. All right, when you're working with other bases, you don't read numbers the same way. Like this base 6 number, don't say 240. Because that, when you say 240, that literally means 2 hundreds and 4 tens, which is not what 240 in base 6 means. 240 in base 6 means 2 36s and 4 6s. So just be careful how you say these numerals when you're in different bases. Don't say them in the way that you're used to saying. Just say the digits. So that's 331, base 5. Don't say 331. All right, back to base 6. Remember, trying to create 13. So we don't need any 36s. 2 6s will get us close. They get us to 12, and we need 1 1. So 2 1 in base 6. So we had 2 3 base 5 and 2 1 in base 6 equal 13 in base 10. And the fourth row, we have 205 provided in base 6. 205 in base 6. So that means we have 2 36s, which is 72. We have no 6s, and then we have 5 1s, which is 5. So this is a 77 base 10 number. Right, so I put that number in there first, base 10. Now we want to make that in binary and in base 5. And keep in mind, I'll put our goal here. We're trying to create 77 out of this. Well, I did as many binary boxes as needed until I went over, right? The next binary box would have been 128. That's too much, so I didn't need to put it. But 164 will get us partly there. We don't need any 36s. That's too much. Adding 16 to 64 is too much. That takes us to 80. So let's add 8 instead. 8 and 64 make 72. Add another 4 makes 76. And I don't need any 2s, but I need one more 1. So 1001101 is our base 2 number for 77 in base 10. Let's see if I put that in. Yeah, 1001101 right there. And now let's do base 5. If I do 3 25s, that gets me pretty close. It gets me to 75. So I don't need any 5s, but I need 2 1s. Also keep in mind that when you're doing these bases, when you're doing base 5, all of the entries, you should never have more than 4 dots in a box. In other words, your numerals should vary from 0 through 4. There should be 5 options, 0 through 4 in this case, when you're doing base 5. If you're doing base 9, it would be 0 through 8 would be your options in each box. Okay, so we finished that one here. 302 was the base 5 representation of 205 in base 6, which is 77 in base 10. Number 7 was to do binary and hexadecimal for the first 40 counting numbers, and I just have our solutions here. Keep in mind that when you're in binary, let me recreate the first 8 of these. So a single 1 in binary corresponds to 1. Here I'm imagining there being, the box here like this, where you have 1s, 2s, 4s, etc. So it's helpful to have that in mind as we put these digits in place. So to do a 2, I need 1, 2, and 0 1s. To do a 3, I need a 2 and a 1. To do a 4, I need 1, 4, no 0s, no 1s. To do a 5, I need a 1, 4, no 2s, and 1, 1. To do a 6, I need 1, 4, 1, 2, but no 1s. To do a 7, I need a 4, a 2, and a 1. And to do an 8, I just need a 1, 8, no 4s, no 2s, no 1s, etc. And you'll notice that as we do the powers of 2, we need to increase by one more digit. So to do 2, I needed 2 digits. The next power of 2 is 4. That's when we needed to go from 2 to 3 digits. Next power is 8. That's when we increase to 4 digits. You can see this pattern happening. By the time we get to 16, I should be looking over here. These are the where I should be looking. Those are the decimal numbers. By the time I get to 16 is when we go from 4 to 5 digits, etc. Okay, in hexadecimal, the digits are, hexadecimal is a base 16, so there should be 16 digits, or 16 numerals, not 16 digits, I take that back. 16 possible numerals for each digit is the better way to say that. We have the traditional 0 through 9, so there's 10 of them, and then we use letters to represent the next values. So an A is going to be a symbol that represents 10 dots. B is going to represent 11, C 12, D 13, E 14, and F 15. Now the reason we use letters instead of just these is because what I just circled are 2-digit numbers, but we need 1-digit symbols for these values. So that's why we use the letters instead. So when you're doing hex, the first 9 digits in hex, the first 9 counting numbers, I should say, match the base 10. But as soon as we get to a 2-digit base 10 number, 10, we use A for 10, right? B for 11, C for 12, etc. D for 13, E for 14, and F for 15. Now keep in mind that we're doing a base 16. So if you were to do a place value table, 16 squared would be 256. All right, so we're really just counting, we have 16 different options, different symbols that can go into each box. And they count how many 256s, how many 16s, and how many 1s we need to make our numbers. Right, so it's just like any other base, except that we're doing a base that's more than 10. That might cause some confusion. So by the time I want to do the numeral 16 itself, I just need, I need 1 16 and 0 1s. So a 1 0 in base 16 stands for 16. In fact, you might have noticed that a 1 0, let's say the base is 3, that stands for 3. A 1 0 base 2 stood for 2. A 1 0 base 16 stands for 16. A 1 0 base 10 stands for 10. There's a consistent pattern here I want you to reflect on. If I want to do 17, so the next number right here, 17 in base 10, well, we need a 16 and a 1. That will give me 17. So 1 1 in base 16 is 17 in base 10. If I need 18, I need 1 16 and 2 1s, etc. Right? So you start to get these, we just keep the 1 in the second position, and we just keep counting up with the first position until I get to right here. So that 1 9 in base 16 really means a 16 plus 9 1s. That's why it's the same thing as 25. 1A means a 16 and 10 1s, so that's 26. Right? 1B means a 16 and 11 1s, so that gives me 27, etc. And then I go up until we get to this 1F. All right, 1F means 1 16 and 15 1s. So 16 and 15 make this 31. Then we get to 32. Well, 32 means I can now just go with 2 16s and 0 1s, right? So 2 0 and hexadecimal, which is base 16, is the same thing as 32. It means 2 16s and 0 1s. 2 16s and 1 1, etc. And then we just keep increasing the first digit until we get to the end of the table. Right down here, when you see 2 8 in hexadecimal, that means 2 16s and 8 1s. So that's 32 plus 8. That's why it's the same thing as 40. The nice thing about hexadecimal is you can represent larger numbers with fewer digits. for example, I could represent 200 in base 10. I would only need these 2 digits to do it. So just 2 numerals to represent larger numbers. So fewer digits needed for larger numbers when you're working with a base larger than 10. It takes up less characters in a string in a computer program, for example. Okay, number 8. This was to express the number 324 in different systems. And here I was just leaning on the notes. There really isn't a whole lot of problem solving to do here. With Roman numeral system, to get to 300, we need 3 C's. To get 20, I need 2 X's. And to get 4, I would have been okay if you had done 4 ones like this. You can do that, but the Roman numeral system has a general rule that if you take a symbol and you follow it with a symbol that's less than it, so a 5 followed by 1, then the operation is addition. But if you precede it, then it's implied you should do subtraction. So this implies do 5 minus 1. And so a 4 is IV. In the Egyptian system, right, the ropes were the hundreds, and the Egyptian system stacked vertically, so 3 ropes gives the 300. Then you needed 2 heel bones, that's the 20, and put some 4 sticks next to it, that's the 4, so 324. The Mayan system, as far as I know, is just 5s and 1s. Bars are 5 and dots are 1. So to get up to 324, we needed lots of bars. So I did 10 bars here, and 10 times 5 is 50. So I just repeated that. Get all these different 50s. Here's a total of 6 50. So there's 300 right there. And then I needed a 10, another 10, and then 4 more to get the 24. And the Babylonian is a base. Let me delete that for now. It's a base 60 system. So it's helpful to make this table base 60, where you have the first box is how many 1s, then how many 60s, then how many 60 squares, or how many 3600s. And then the entries inside these can be anything from 0 up through 59. But then they have symbols for these values. Let's go back to our guided notes and go to the last page. Here we go. And we're just going to copy and paste after we figure out what numbers we actually need. So let's go back to the homework assignment. I don't need any. This is too large. We're trying to create 324. So definitely we're going to have nothing, no 3,600s. How many 60s though? So we have to figure out how many 60s go into 324 without exceeding it. So we need 5. And that 5 times 60 is 300. And then we need 24 ones. And it's okay to put 24 dots in this box here because we can allow up to 59 dots per box because this is a base 60 number. So there would be 5 dots here if you're doing dots, and then 24 dots in here. And this would mean 5 60s and 24 ones, and that represents this 324. Yes, but let's not use dots. Let's use the Babylonian symbols to represent 5 and 24. Okay, so 5 is these 5 symbols here. I'm just going to copy and paste that. Or you can draw them by hand if you like. So we need this symbol here in this position that represents 5 60s. And now we need a 24 symbol, which is 2 10s and 4 1s, given by this collection of symbols. Okay, and so there it is. We have, this represents 5 60s and 24 1s. And normally they would just have the symbols, none of the stuff here would be visible. It would look like this, and say put those symbols next to each other, and that's read to be 2 different digits, if you will, a 5 and a 24, and the place values are 5 60s and 24 1s. Okay, and